How is it possible for a spacecraft like Voyager-2, which was launched in 1977 and visited the 4 outer planets, to travel nearly 17 billion kilometers in 40 years while having essentially little fuel? With technology from the middle of the 1970s, Voyager-2 had already passed through Jupiter, Saturn, and Uranus by the time it arrived at Neptune. It had also traveled 7 billion kilometers and was still within 100 kilometers of its destination. In the movies, spacecraft simply seemed to fly anywhere they wanted to go and be there quickly, but in our version of reality, travel is considerably more difficult and takes a great deal longer. Can you picture Spock telling Kirk, "We've just passed Pluto, almost home, only 9 years to go," just in case you missed the significance of the fact that it took the New Horizons probe 9 years to travel the approximately 5 billion kilometer distance between Earth and Pluto? At the time, it was one of our fastest spacecraft. The key to all of this is understanding how gravity functions and how it impacts not only you and I, but also everything in the cosmos. It might seem like an insurmountable endeavor, but when you understand how space and physics work, it becomes a set of procedures, science fact instead of science fiction. The principles of planetary motion were initially formulated by the German mathematician Johannes Kepler 400 years ago, and Isaac Newton utilized them as the foundation for his laws of motion and the development of classical mechanics. The method by which we can anticipate with remarkable accuracy the motion of everything in the solar system and beyond, including planets, comets, asteroids, and spacecraft. According to Newton's first law, unless a force acts upon it, an object at rest or moving in a straight path will remain in that position. For instance, a rock on the ground won't move by itself unless another object picks it up or moves it. If that identical rock were in space and traveling straight ahead, it would not alter its rate of motion or course without the application of an outside force. Gravity, whether it comes from the sun, a planet, or even another rock, is always a force acting on a moving entity in space. Any object with mass produces a gravitational pull, which increases with mass. The speed of a moving object is the additional factor. According to Newton's second law, an object's speed will change if a force is applied to it. This law is reversible, thus when an object's speed changes, a force is produced. This explains why an asteroid striking the planet at 17 kilometers per second can be so catastrophic. The abrupt shift in velocity causes the asteroid to unleash a tremendous quantity of kinetic energy. A projectile that is fired on Earth while being parallel to the ground will eventually return to the ground due to gravity. When a projectile is fired quickly enough and keeps moving at that speed, it is still moving in a straight line, but as the gravitational attraction of the Earth increases, it bends its trajectory until it is in orbit around the planet. In other words, the force of gravity pushing a projectile back to Earth equals the force of the projectile trying to go on a straight path. This is how satellites and space stations maintain their orbits, although the minuscule amount of drag caused by a very thin atmosphere located far above the planet also has an impact. They slow down as a result, and as the force holding them in their orbits weakens, the scales eventually tip in favor of gravity. As it drags them lower and lower, the atmospheric drag increases, slowing them down even more. If they don't periodically pick up speed to extend their orbit, they will eventually fall back to Earth. A spacecraft's orbit will get longer and more elliptical if its speed is increased, but it will always pass past the location where the speed was initially increased. Our spacecraft will enter an orbit around the Sun and escape the gravity of Earth if its speed is sufficiently boosted. The orbit of our spacecraft can intersect the orbit of a planet using the Hohmann transfer approach, which is one of the most popular ways to move from one moving body to another, although there are now more effective but much longer ways, like the low-thrust transfer method. If we get the speed boost correctly timed with an approaching planet in what's called the opportunity, we can get the orbit of our spacecraft to intersect the orbit of a planet. Once there, our spacecraft can either orbit the planet or utilize its gravity to slingshot around it. This technique is known as gravity assist and increases the spacecraft's speed in relation to the Sun. Gravity assist uses a planet's gravity to tug on our spacecraft as it approaches and can be used to increase or reduce a spacecraft's speed, so changing the size or direction of its orbit. Our craft will accelerate if it is traveling in the same direction as the planets. Its speed will drop if it travels in the opposite way, and depending on how it approaches the planet, it may even shift its trajectory and depart in the opposite direction. However, as there is no such thing as a free lunch, and because of the law of energy conservation, any energy our craft acquires must be offset by energy lost by the planet. Jupiter's orbit around the Sun slowed when the travelers used Jupiter to increase their speed to reach Saturn, but only by a little over 1 foot every trillion years. With the help of gravity, we can travel from planet to planet farther and farther away, speeding up our craft along the way until it reaches escape velocity, at which point we'll be moving quickly enough to escape the Sun's gravity and exit a solar system, just as Voyager 1 has already done. It will take Voyager 40,000 years traveling at a speed of more than 60,000 kilometers per hour to arrive at the location where the Sun's gravity is no longer dominant, but the Sun's gravity will still exert a pull on the craft and slow it down. In fact, the Sun's gravitational effect extends outward by about 2.5 light years. According to Newton's third law, every action has a corresponding and opposing response. Basically, a craft goes forward by the thrust of an engine pushing backward. Some individuals believe it is difficult for them to work in space since the thrust of a rocket pulls against the Earth or the atmosphere. This is obviously false because our thrusters and rockets continue to operate in space even if there is nothing for them to push against. We utilize this thrust to raise or reduce speed and so change the orbit of our spacecraft. We also use thrusters to move the spacecraft in the X and Y planes to orient its antenna with the Earth or direct its cameras at a target. The next thing we need is an accurate model of the solar system, which will show us where the planets will be in relation to not only the Sun, but also to each other and other objects like comets and asteroids. Once we understand how gravity affects our spacecraft and that we can use it to move from planet to planet, the planetary ephemeris, which functions as a kind of timetable for all the major bodies in the solar system and provides information on each body's position with respect to the Sun at any given time in both the past and the future, is the basis for this model. We were the first to collect this information over the course of centuries after being founded by the Babylonians in 1200 BC. Ephemeris for several centuries in the future can be calculated using celestial mechanics. It would be hard to plan space missions without knowing where the planets would be in the years to come because space missions, like the Voyager ones, endure for years or even decades. However, these ephemerides are not perfect because of the gravitational influence of undiscovered asteroids and maybe an undiscovered planet X beyond Pluto. Over the past 20 years, NASA has revised its ephemerides as new information has become available. Therefore, being aware of the future positions of the planets and how our spacecraft will move through space permits navigators to plan our spacecraft's trajectory with extreme precision. This was demonstrated by the Voyager missions, which used planetary ephemeris to identify a triangular alignment of Jupiter, Saturn, Uranus, and Neptune that occurs only once every 175 years. Gary Flandreau made this discovery in 1964 while working at JPL, and it helped the planners create the Grand Tour. If they launched in 1977, this would enable one spacecraft to go to all 4 planets utilizing gravity assistance, reducing the mission's duration from 40 years to less than 10. Due to financial constraints, Pluto was originally supposed to be included in the Grand Tour. However, the New Horizons spacecraft visited Pluto in 2015. The first spacecraft to leave Earth in 1977 on a grand tour of the 4 outer planets and eventually leave the solar system's orbit was Voyager-2. Later, the Galileo, Cassini, and New Horizons missions used the same gravity assist approach. 3 weeks after Voyager 2, Voyager 1 took off on a more direct path to Jupiter, Saturn, and Saturn's moon Titan. However, doing so would send it on an upward trajectory out of the solar system and into interstellar space. It was turned around as it was leaving so that its camera could look back at Earth and snap one more series of pictures. These were the solar system's furthest photographs ever shot, and one of them showed Earth's location within it. The iconic pale blue dot, as Carl Sagan dubbed it, was captured in the middle of a lens flare at a distance of 6.4 billion kilometers while gazing down at a 32-degree angle towards the solar system. It was only 0.12 pixels in size. We now have a strategy, but we still need something to direct our spaceship along the intended course. They do this by using an inertial navigation system, which is essentially a very accurate network of gyroscopes, accelerometers, and other sensors that can track a craft's motion in any direction in space. The navigators can determine whether the craft is on course using this information. However, because they are mechanical devices, inertial navigation systems are susceptible to a phenomenon known as integration drift, which causes minute mistakes in the gyroscopes and sensors. Since they calculate their position as they go from the latest previously estimated position, the mistakes accumulate over time and become more significant the further they travel. When entering an orbit with an accuracy of just a few kilometers, the error in a decent system is less than 1.1 kilometers per hour, so if a trip to Mars took 8 months, or 5,760 hours, the inaccuracy would be roughly 6,300 kilometers by the time it arrived at Mars. Another fixed reference system, the stars, are required to counteract the integration drift. Spacecraft employ optical sensors and cameras to establish their position and reset the inertial navigation systems, much like maritime navigators would with a sextant. When the onboard navigation system drifted during the Apollo missions, the crew used a space sextant to rectify it. A star tracker was employed on the Voyager probes to look for an extremely bright guiding star, in this case Canopus. Additionally, it contained a sun sensor that could be utilized with an Earth radio signal. Modern spaceships have more advanced systems that use cameras to search the target and known objects like planets, comets, and asteroids. Even with the best laid plans, things can change at any time. Deep spaceship may potentially be impacted by other forces. Timing is crucial when adjusting for factors like the solar wind, which is the passage of charged particles from the sun that can progressively alter a spacecraft's direction over time. Along the way, our spaceship must reach specific locations in space within a very constrained amount of time. If you are off by more than a few minutes when approaching a planet at 30 kilometers per hour to use its gravity to swing by and change direction, you risk being dragged into the planet by its gravity or undershooting the intended trajectory. NASA uses the Deep Space Network to communicate and calculate a craft's speed and distance. This is a global network of radio telescopes designed to keep a spacecraft in constant communication with at least one of them. With the use of the Doppler effect, an extremely precise atomic clock, and the reception of a radio signal from the object, it is possible to determine the craft's distance from Earth to within 3 meters and its speed to within 180 millimeters per hour. By combining all of this data, we are now able to send space probes with incredible accuracy, allowing us to do things like take close-up pictures of Pluto within a 2-hour window, 9 years after launch, 5 billion miles away, and when we only had 1/3 of Pluto's orbit mapped. We can also now land on a comet, as we did with the Rosetta probe and its Philae lander. Using the techniques we've discussed, 5 spacecraft have now reached escape velocity and are the furthest objects made by humans. New Horizons, Voyagers 1, 2, and 10, 11, and Pioneer 10. It's incredible to consider that all of this was based on theories that were created hundreds of years ago by observation alone and the desire to understand how the heavens function before we even considered the possibility of entering space, much less using gravity as our primary propulsion system. The capacity to calculate planet orbits is a crucial component of planning any future space missions that humans may undertake. Thanks for watching, and don't forget to like and subscribe.